So hi, good evening. Uh, we'll just wait for 3 or 4 minutes and then we can start, okay? So in the meantime, can you tell me if my screen is visible? Are you able to see the slide? And is my voice audible? Can any one of you please unmute and tell? Sudarshan or Jeevan ready?
Yes, sir, it's visible, sir.
Okay. Thanks, Sudarshan. Thank you. We can just wait for 2-3 minutes and we can start. Okay, so I think we can start for today. Um, Let me go to my screen and put it in full screen. So, good evening, everyone. I'm Nand Kishore from the Department of Electrical Engineering, IIT Delhi. So, welcome to the problem solving session for the course Advanced for Electronics and Control. This is for week 3. So, in this week, I presume you covered the leftover topics from single phase rectifiers, and so far you are experts, I guess, in controlled and uncontrolled single phase rectifiers. And then in this week you focused more towards three phase rectifiers. So you studied about 3 pulse and 6 pulse rectifiers, controlled and uncontrolled, using diodes and ACRs. And then you also forayed into multi-pulse converters, wherein you covered for example, 12 pulse rectifiers and stuff. So wherein you have two full bridge rectifiers connected. And then you also briefly saw about the effect of source inductance and how it impacts the output voltage of the circuit. And so with the variation in source inductance, what happens to the dip in the output voltage you see? And you, of course, know that there is an overlap angle that comes into play due to the source inductance. So you stated about that. So what would be that overlap angle for different kinds of converters, for single phase as well as three phase converters, right? And then at the end, you studied about what are known as PWM rectifiers, wherein you try to emulate a perfect rectification, right? Like without any distortion factor or without any harmonics. You try to get a pure sine wave at the input as well. So that's the idea of studying these converters, right? So you study rectifiers, you of course know that the power factor is going to be very low, right? You have the power factor is 0.9 cos alpha or something like that for diode-based rectifiers. So the emphasis towards power electronic research is on, okay, so how do I do rectification while maintaining my input current to be sinusoidal, correct? So the idea is, uh, here let me first disclose the idea. The idea is that, okay, so you have an input which is purely sinusoidal. It's a pure sinusoidal wave, right? And you want the output to be a flat DC, correct? So this is something you want. At the same time, of course, you know that, okay, if you have a rectifier as the load, I mean a resistor as the load, you of course know that the current, the output current, as you say, is going to be something like this, right? That's going to be V naught by R. Now the point is you want your I in, right? You want your I in to be something like this. So this is the perfect scenario, right? Perfect scenario for rectification. Your V in is going to be a pure sine, right? And your I in is also going to be a pure sine. So which means that if you have pure sine waves as voltage for input voltage and input current, you of course know that the fundamental or the 50 hertz component is going to be 100%, correct? And the harmonics, third order or fifth order, seventh order, and so on, you want them to be zero, correct? This is the ideal scenario. This is something you want, correct? However, um, however, you of course know that this is something that's not possible, right? So what you generally see is something like, okay, let me redraw this again. So this is your V in and this is your V naught, and let me take blue. Okay, correct. And so you expect this to be your V naught and a similar looking current, right? Something like this as your I naught. Okay, so from this you can actually infer that you can actually infer multiple things from this. One thing is, of course, this is the ideal case. Okay, so what you infer is, okay, the input power is going to be V in times I in. And you know that Vn consists of only Vm sine omega t, correct? No harmonics. And In is going to consist only of Im sine omega t, correct? So the entire power is going to be useful power. There is no losses in the form of harmonics, correct? So that's something you want, right? So you don't want your current to be having components like, okay, sine omega t, omega 1 t plus 3 omega t plus 5 omega t and so on. You don't want this, correct? So this is the idea, or this is how power electronics is graduating now, proceeding right now. That is okay. So how do I obtain rectification such that my input current is purely sinusoidal, so that my power factor remains unity, right? So this is the idea, right? Power factor should remain unity, and of course, THD should tend to zero. Okay. So towards realizing these circuits, you have circuits known as PWM rectifiers. So actually, PWM rectifiers are such power electronic circuits which make this possible. Okay, how is this possible? You will probably learn in your advanced courses, probably when you go for master's degrees and stuff, you will know how these operate. Okay, so these are totally different to your ACR based rectifiers. Okay, so you use the concept of DC-DC converters in order to create these rectifiers, PWM rectifiers. Okay. Okay, anyway, so that's for later. But anyway, the idea is if you use PWM rectifiers, you can get this, you can emulate this. Okay, power factor will tend towards 1 and the THD will tend towards 0. And that's something you want, right? And of course, the efficiency will be above 96% conversion efficiency. Okay. Okay, but I guess right now you know that, okay, single phase rectifiers, if it's DBR diode bridge rectifiers, the power factor is going to be 0.9. And if it's three phase, you know that it's going to increase. It's going to become 0.955 and something like that. Correct. But how do you make it one? How do you make it almost 1.99 or something like that? So the answer is with PWM rectifiers. Okay. Okay. So this is something you saw, introduction to PWM rectifier. So this was what you covered in the past week. Okay. So based on these topics, we will be having a problem solving session today. So of course, there will not be any problems in PWM rectifiers because you didn't go deep into that. But we will be seeing adequate problems from single phase and three phase rectifiers, and of course, the effect of source inductance. Okay. Okay, so before we even start solving the first problem, I wanted to give you an interesting problem, right? It is something related to power factor and stuff. So since you have done this, I guess you should be able to appreciate the problem. Okay, so I will just write down the problem over here. Okay. So question, let me call this question 11. The reason being that I have 10 problems in this slide. Okay. So the question is, it's a very simple question. So you have an AC source, you have a diode, okay, and then you have a rectifier. I mean, you have a resistor, beg your pardon. Okay, so you have your resistor, and this is Vs. Okay, I define Vs as Vm sine omega t. It's just a single phase AC source. Okay, single phase AC source. Okay, R is a pure resistive load, and this is just a diode. Okay, so question is, find the factor of the circuit. Okay, so I will also give you the options. Option is 1, A 1, B 0, C um, C C will be 0.9 and D will be 0.707. Okay, so what's the answer? So your intuition should not tell you that, okay, so you are seeing a resistor over here. So because it's a pure resistive load, let me take this. Okay. So if you do this, you're going to lose your marks. Whatever be the negative marking, okay, it's going to result in -2 or -1 or whatever. Okay, so give attention to the problem. So the point is, see, there is a diode over here, correct? So when you need to investigate what this diode does. Okay. So first you try to understand what is power factor. Okay. So power factor, if you see the definition of power factor, it's going to be over here in a diode circuit. It's going to be V naught RMS by Vs RMS. That is the RMS value of the output voltage divided by the RMS value of the source voltage. Okay. So we know what is the Vs RMS, right? So what is Vs RMS? Vs RMS is going to be Vm over root 2. This is something that's straightforward, right? It's coming from here. Vs is equal to Vm sin omega t. Therefore, Vs RMS is going to be Vm over root 2. But what is V naught RMS? Correct? So this you need to find out. I think you have done this in the course, but nonetheless, I will do for this problem. But one thing I will tell in this tutorial session is that there are a lot of formulae over here based on which the numericals are solved. So it would be better if you can somehow relate the formulae with what you have studied. Okay, so it's not, of course, you understand that it's not possible for me to derive each formula for each question, right? Anyway, but for this, I'll just write it down. Okay, so you had diode, a resistor, and Vs. Okay, so let's take the generic case of this being an SCR. Diode is of course with alpha equal to 0, right? So let's take an SCR. Now, if you take an SCR, what happens? So if you draw the waveforms, if this is your input voltage, then your output voltage is going to be, okay, it will start conducting after alpha, and then it goes to 0. Correct. This is something that's straightforward. You studied this in the last class itself, right? And let's say you are having a pure resistive load, therefore your current will also follow a similar profile. Correct? Okay. So this is going to be your V naught, comma I naught. So the idea is, as I told, power factor is what? V naught RMS over Vs RMS. So the point is you just need to find out the RMS of this particular waveform, and then you are done with the problem, right? Okay. So what is the RMS value? By definition, Vrms is given by 1 by t integral 0 to t, I mean, whatever is the period, I mean, I will write it as t1 to t2, and then whatever is the function, right? So V naught square d omega t, correct? So in the over root, right? Over power 1 by 2. So it's going to be 1 by 2 pi, which is the total time period, correct? So 1 by 2 pi integral. So what should be the integral? Integral will be from alpha to pi, right? So integral from alpha to pi. And what is this waveform? This waveform is going to be Vm sine omega t, the whole square d omega t. So I'm not going to solve this. You will eventually end up with 1 by 2 pi or root over 1 by 2 pi. And then Vm integral sine square omega t, or in sine square omega t is 1 minus cos 2 omega t by 2. So you just take an integral of that one, and you will actually end up with pi minus alpha plus sine 2 alpha by 2 whole root. Correct? Of course, 1 by 2 factor will come, so into 1 by root 2. So you will actually end up with Vm by 2 root pi into root over pi minus alpha plus sine 2 alpha by 2. Correct? I think you are all aware of these formulas, but anyway, the first one alone I thought I will just do. Rest I will not be doing anyway. Okay. So VRMS was 1 Vm by 2 root pi into root over 5 minus alpha plus sine 2 alpha by 2. Okay. So with alpha equal to 0, what happens? VRMS is going to be Vm by 2 root pi into pi plus so sine 0 is going to be 0. So it is going to be root over pi. So this and this get cancelled. So you end up with Vm over 2. Therefore, the power factor. So what is the power factor? As I told, V naught RMS over Vs RMS, right? So V naught RMS is Vm by 2 and Vs RMS is the source, which is Vm over root 2, right? So you will end up with 1 by root 2, which is 0.7071. Okay. So the power factor of the circuit is 0.7071. Okay. So over here, what is the answer? The answer is D 0.707. So please see the, if you see the circuit, don't just directly jump into conclusion that, okay, there is a resistive load over here. Let me click one. The answer is wrong. You see the impact of a diode, right? What it does, it actually stops your current. It does not allow the current to flow for the entire full cycle, right? And that's the reason you get a waveform something like this. Therefore, your um, value is also different, correct? Your power factor is also different. Okay, of course, you understand that this current is going to consist of a lot of harmonics, right? Because it's not a sinusoidal current. Okay, so I think you get this. And of course, for any other value of alpha, you can compute from this expression, right? So you can just substitute this over here. So generically, we can conclude that V naught RMS by Vf RMS is going to be your Vm by 2 root pi into root over pi minus alpha plus sine 2 alpha by 2 whole divided by Vm by root 2. Correct? So your um so your Vm and Vm get cancelled, right? So and then this root 2 cuts over here. So what you end up with is 1 by root 2 pi into root over pi minus alpha plus sine 2 alpha by 2. So for any other thyristor circuit with a resistive load, this will be your power factor. Okay. So please do understand what the impact of a thyristor or a diode can be, right? Okay. Mm. Okay, so before I move into my problems, I think I will solve some other problems which can be written and solved so that anyway, the solutions for all of these are given in the slide, so you can have a look at them even later. I think it would be better if I actually solve in front of you, right? Some problems. So I have got a few problems over here which I will solve. Okay. Okay. So this will be question 12. Okay. So the question is calculate the power dissipated in the load if Vs is 230 volts, R is 10 ohms, L is 10 millihenries, and firing angle is 30 degrees. Okay. So what is the circuit? So the circuit is something like this. Okay. I'm sorry. So the circuit is something like this. Okay. Okay. So the question is simple, right? So this is your alpha, correct? And this is your Vs. This is your freewheeling diode over here. You have an R and then L. So the entire output voltage will be appearing over here, correct? So calculate the power dissipated. So first understand the question. The question is calculate the power dissipated. So dissipated means the person wants to tell, or the question wants to tell, that this is going to be a loss. You tell, right? Like this is the total power loss or the loss dissipated. So where will the loss get dissipated? The dissipating element is this resistor, correct? So this R is a dissipating element. So if they ask you to find out the power loss, you just need to find out what is the power dissipated across this resistor, correct? And what is the power dissipated across this resistor? So you have your R, and then you can calculate what is your V, right? So it's going to be V square over R, right? Now the question is, okay, so it is V square over R, but in V it can be either V average or V RMS, right? And these two are different, mind you, for these converters. So how do you find out? So the answer is it will be RMS value, correct? Why? RMS value is the parameter which is responsible for any current any power dissipation. Okay, RMS current leads to losses and heating, correct? So if you remember from your class 12 itself, so how do you define RMS? You tell it's the root mean square, but you tell that that is the equivalent amount of current which causes the resistor to heat up, correct? So always, if the question is about power dissipation or heat or the loss, you always need to take the RMS value. Okay, so have this as a thumb rule. Always you need to take the RMS value. Therefore, the answer is VRMS square over R. Simple, right? Okay. So now that we have sorted it out, we need to find out what is VRMS, correct? So for this circuit, so what is this circuit? You have a thyristor and then you have a freewheeling diode. So if you have a freewheeling diode, you can understand that your current cannot go negative, correct? Generally, if you have an inductor, what you might be seeing is something like, okay, so it starts conducting and then something like this. This is what you will see if you have an inductor. But since you have this freewheeling diode, it will not allow the voltage to go negative. Therefore, your waveform is going to be simply something like, correct? Something like this red waveform. Right, this is your alpha, this is your pi, this is your 2 pi, this is your V naught, and this is your Vs. So again, you just need to find out the RMS value of this waveform and then you are done, correct? So what is the RMS value of this waveform? We just saw in the previous problem that the RMS value is given by this. Vm by 2 root pi into root over pi minus alpha plus sine 2 alpha by 2. So I'll just write it down over here. So V naught RMS is Vm by 2 root pi into root over pi minus alpha plus sine 2 alpha by 2. Okay. So please, I urge you not to just see me solve. Rather, it would be better if you take out your calculators and you also start solving, because until and unless you solve by yourself, you're not going to get it. Okay. So what is your VM? They have given VS as 230 volts. So always remember another thumb rule. If they just mention the number, it is always your RMS value. Okay. If they just mention the number without telling anything else. If they tell it's 230 sine omega t, then it is your VM. Correct? It's your maximum value. But right now over here, they have just told VS is 230 volts, nothing else. It means that it's the RMS value of the input voltage. Any AC quantity, if they just give the number, You take it for granted that it's the RMS value. So what's Vm? It would be 230 root 2 divided by 2 root pi into root over pi minus alpha, right? So what is 30 degree? Pi minus pi by 6 plus sine 60 by 2. Okay. So if you solve it, what happens? Please again, you guys can solve. If you get the answer, you can also tell me. Okay. So what will be your V naught RMS? It will be okay. So it's going to be 160.27. If you find any discrepancy in whatever I'm writing, the values or something, please go ahead and you can stop me at any point of time. Okay. So since this is your V naught RMS, your power output or P dissipation is V naught RMS square over R, right? So 160.27 square over 10, and it's going to be around 2.57 kilowatt. Okay, so this is the power dissipated in the resistor. Got it? So please, if you have any doubts, you can stop me at any point of time, of course. Okay. So next we will go to question 13. So is this fine? So you just found out the VRMS value and then VRMS square over R. It's going to be this much. Okay. Okay. So question 13 is going to be the same circuit in the sense that, okay, so you have a thyristor and then you have something like the source and then you have a load. They have not mentioned. Okay, so they have mentioned. So this is the load and this is Vs. This is your thyristor and this is your freewheeling diode. So for the converter shown in figure, for the rectifier shown in figure, rectifier shown R is 10 ohm and L is 0.05 henries. So R and L are over here. Okay. R is 10 ohms and L is 0.05 henries. The maximum value of the supply voltage, they have mentioned it explicitly over here, therefore this is a maximum. Okay, so the maximum value of the supply voltage is 325 volts and the output voltage is actually 70 volts. Okay, so find alpha or find the triggering angle or the firing angle for this thyristor. Okay, so this is a pretty simple question. You just know the output voltage average value and of course it's the average value, right? And of course, the thumb rule is if just a number, if it is just a number, in AC quantities, it will be the RMS, and in DC quantities, you can take it the average. Okay. Anyway. Okay. So this is a pretty simple problem. If you know the formula for V naught, you are done with the answer, right? So what is this converter? This is a single phase half rectifier with freewheeling diode. Correct? So what is the V naught? So V naught is Vm over 2 pi into 1 plus cos alpha. Okay. Therefore, 70 is equal to 325 over 2 pi into 1 plus what's alpha. Therefore, your alpha is, you can calculate, please. Hmm. Hmm. So you will be ending up with alpha of 69.31 degrees. Right? Is this fine? Okay.
Yes, sir, one doubt.
Yeah.
Here
Please,
in
please.
place of VM, previously we used 320 voltage into root 2 times, right? But here we are using direct.
Correct. See. In this question, okay, I have not written the entire English question. In the question, it is explicitly mentioned that I have just written as VM as 325. In the question, it is explicitly mentioned that the maximum value of input voltage is 325 volts. It has been mentioned explicitly in the question. Okay. That is why I have taken it as 325. Let's say they did not tell anything about this. They just told the input voltage is 325 volts. Then I would of course take it as RMS. Here they have mentioned it explicitly, and that's why I'm taking it. Okay.
Yeah,
So
got
your
it.
so your VS will be 325 sine omega t. Yeah. Okay. Okay. Mhm. So let me move on to the next question. I'm trying to solve different problems as possible for you. So, okay, again another dissipation question, but this time for a different converter. So this will be question 14. Right. Okay. So this is a purely resistive load. Okay, and this is your BS, right? And you have your diodes, and this is your. So this is actually what? This is your single phase full bridge rectifier. So in this circuit, they have given R as 50 ohms. Okay. Alpha is what? Alpha is 0. Correct? Because these are all diodes. So this will come handy while solving, right? And they have mentioned explicitly that the supply voltage is 200 sine omega t. Okay, then you can understand this 200 is actually your VM, right? They have mentioned it as 200 sine omega t, where omega is 100 pi, right? That means that F is 50 again. 2 pi F, right? Omega is 2 pi F. Okay, so omega is 100 pi radians per second. So what is your P out? So here there is no question of dissipation or the total output power or something. Anyway, you have only a resistive load. So just find out what is P out, okay, which is VRMS square over R, right? So P out is V naught RMS square over R. Okay, so how do you find out V naught RMS for this particular case? So this is one wave of your input voltage. And how is your output going to look like? Your output will look like, sorry, correct? This is how your output is going to look like 0, alpha, pi, pi plus alpha 2 pi. V naught Vs, right? Do we need to draw this again or is this fine? Okay, I think it is fine now. Okay, so how do you find out the RMS RMS? So V naught RMS is root over 1 by 2 pi, not 1 by 2 pi. You see that this is repeating after every pi, right? So you can take the total time period for this as pi. So root over 1 by pi and then integral alpha to pi Vm square sine square omega t d omega t. Correct? Fine. So if you solve this, you are going to end up with V naught RMS is equal to root over 1 by pi integral alpha to pi and Vm square sine square omega t, right? So sine square omega t is 1 minus cos 2 omega t by 2 times d omega t. Okay. Okay. So you are going to end up with Vm by root 2 pi into root over pi minus alpha plus sine 2 alpha by 2. So this will be your V naught RMS. Okay. So what is your V naught RMS in this case? It's going to be Vm was given as 200 volts, 200 over root 2 pi into root over pi minus alpha. So what is pi minus alpha? So alpha was 0 over here. So pi plus sine 2 alpha is again 0. Therefore, it's going to be something like this, correct? So it's going to be 200 over root 2 volts. Okay. Therefore, your P loss is going to be V naught RMS square over R, that is 200 by root 2 over whole square over R was 50 ohms. So this will turn out to be this will turn out as, of course, yeah, 400 watt. Got it? So any questions over here? So I think this is a pretty simple question. Just that they have given the single phase full bridge rectifier with a pure resistive load, and alpha is of course 0 because it's diode based. Okay. So you just need to find out. I did it for the generic case so that you are able to solve it even if alpha is a non-zero value, correct? So in this case, you saw that, okay, so you just substitute alpha equal to 0, you end up with Vm by root 2. Yes, you just end up with Vm by root 2. You put alpha when you put alpha equal to 0. Okay. So this was the loss. Okay, so we can go to the next question. Okay, meanwhile, what is the power factor of the circuit? If someone asks similar to question 1, so what is the power factor? Power factor was V naught RMS over Vs RMS. Correct? So what is V naught RMS? We saw that V naught RMS is Vm by root 2. Correct? And what is Vs RMS? Vs RMS is also Vm by root 2. Therefore, the power factor is unity. Okay. So this is something that's interesting, right? So for this circuit, you are seeing that, okay, the power factor, if you see from the input side, for this circuit, it's unity. Correct. The answer would be 1. Power factor is unity, right? However, for the first problem that we saw over here, right, the power factor was not unity, it was 0.707. We just had one diode in series, correct? However, in case you have, in the case of a full bridge, you have a power factor of unity, right? This is something that's interesting. Okay, got it. If any doubts, you can of course ask me. Okay, we can go on, move on to the next question. Okay. So this is something actually that's interesting, and I think you may be aware of it from the lecture slides, because I think it was covered in the lecture slides. But anyway, we will be seeing this. So the question is, find the yeah. So find the THD, then fundamental displacement factor. I'm writing it as FDF. It's actually fundamental displacement factor. Fundamental displacement factor. So find the THD, fundamental displacement factor. And the power factor, right? And the power factor for a single phase full wave rectifier with RL load. Okay. So this is the question. So this seems like a theoretical question, but there is a reason why I'm keeping this question, right? Because if you get to know these, then you can actually solve a lot of problems. Okay. Okay. So what's the circuit? Right? Correct? It's your I naught, V naught, or L, and it's your Vs. Okay. So just need to find out the voltages, and then you are done. So let's draw the waveforms. Okay. Hmm. So there is something that's interesting that's going on over here. Okay. So you know, of course, that your input voltage one cycle is going to be something like this, right? So how would your output look like? Your output voltage will look something like, of course, I'm taking the generic case. Okay. Full wave rectifier. Okay, I will draw these thyristors. Okay, I'm taking a generic case. So this is alpha and this is pi. So what will happen, of course, is that it will increase and then go over here. But since this is an RL load, what you will see is it goes a bit negative, right? till some point and then it goes back to 0. Okay. So you may be aware that this is what is called as beta. Beta is your extinction angle. And then there is again your pi plus alpha. Of course, this is not to scale, but still I think you understand. Okay. So this is your beta. And this is your pi plus alpha. So this is your pi plus alpha. Okay. Just need to plug in. Okay. So this is your pi plus alpha, right? Okay. So this was your V naught and your I naught will look something like, okay, so it will start from 0. It will increase. It will of course increase. And then it will reach 0 here, remain 0. And then it will again follow this cycle. Okay. Okay. So what about your source current, right? Because we are talking about THD, fundamental displacement factor and power factor, we need to know the source current, right? Because after all, your source current is the one that's alternating. Your output voltage and your output current are going to be a DC quantity, right? So how would your source current look like? So the point is, so let's say that your load current was almost constant. Here I drew it as something varying like this, right? But let's say your inductor value was really high. Okay. So let's say your inductor value was really high. In that case, you will see that this current is almost constant, right? You will see that I naught is almost constant. Why? Why I naught is constant? Because if your inductor is really high, if your L is really high, then what happens is L always opposes change in current, right? Like it opposes changing current. Correct. So let's say you have motor applications or something like that. You always want you don't want sudden changes in current, right? Like you don't want LDI right? Because it will give voltage spikes. So what you want is a smooth constant current, something like this. Okay. So if your current over here or the current that's coming over here, it's something like this, then what do you see over here? What do you expect to see over here? You just expect to see a square wave, right? Okay. So I told you that you had something like this. And your inductance is really large, that the current that is coming over here, it is a flat DC. Okay. If your current is a flat DC, then what do you see as expect to see as the current over here? You should be seeing a square wave, right? Correct. Something like this. Right. So this is what you expect to see in the, yeah. Hello. Okay. So this is something that you expect to see, right? Okay. So then what happens now that you have your input current is something like, so you understand that because this is a square wave and you know that a square wave consists of a lot of harmonics, right? A square wave typically consists of a lot of harmonics. So you can very well find out what is your fundamental displacement factor, power factor, THD and stuff. You can find this out. Okay. So go back to Fourier. What is the Fourier expression for? What is the Fourier
Hello,
expression for? Yeah.
hello, sir.
Yeah.
Like
Tell me.
this constant current, like the like we assume that the inductor value is very high and the current is constant, right? But
Correct.
but my current constant current, but my current will also change based on my firing angle also, na sir. Like if my input voltage is very less, then maybe my current won't be constant.
Um, yes, I agree with you. It should change with your firing angle. Correct. It should change with
Yes, sir.
firing angle. See, this is the effect is something that you expect to see as the current through these thyristors will change. That is agreed. Sorry.
Yes, sir.
Okay. But the point is over here in the load side, if you consider purely in the load side, okay, this inductor current should be constant, correct? Let's say you assume a very large inductor. This is very small and this is very large, correct? So the inductor will try to draw a constant current somehow. Agreed? So what I'm doing is this entire portion over here, right? This entire portion is okay. You have SCRs over here which have a fixed firing angle, but what I'm assuming is in the equivalent circuit, I have some element over here, and I have an inductor which has a constant current. Okay. So over here, I'm trying to find out what will be the shape of the current. Okay. I agree that this will not happen in reality perhaps, but still it makes for finding out the expression for these, this assumption is valid, right? I'm assuming that, okay, so these are just switches which can make this DC current alternating over here. Got it?
Yes, sir.
Okay. Okay. So since you have a square wave, how do you analyze it in Fourier? Your source current can be written as something like n equal to 1, 3, 5, and so on. And this will be 4, and this is I naught, correct? So this is your I naught. So 4 I naught by n pi sine n omega t, correct? Of course, there will be an angle phi. Why? This phi n is tan inverse n omega L by R. Okay. So this is just from Fourier series. This is coming from Fourier. Okay. It's coming from Fourier transform. Okay. So what is your fundamental component? IS1. It's going to be 4 I naught by n pi. Right. And if I want my RMS, it's going to be whole divided by root 2. Got it? So this is your fundamental component at n equal to 1. Okay. So from this, you should be able to tell what is your fundamental displacement factor. Correct. So your fundamental displacement factor is what? Fundamental value divided by the whole value, RMS. So what is IS1 RMS? 4 I naught by n pi over root 2. Right. And what is your IS RMS? So what is the RMS of a square wave? It is just the amplitude, right? It's going to be I naught. Correct. So you are going to end up with 4 over n is of course 1, 4 over root 2 pi. Correct. So 4 over root 2 pi, it will give you around 0.9. Okay. Got it. So fundamental displacement factor is 0.9. Any doubts so far? If you have any doubts, you can tell. Or we can go ahead. So fundamental displacement factor is done. Correct. Just give me a second. So G is I'm sorry. So this is not your fundamental displacement factor. This was your distortion factor. I got my definition wrong. So this is your distortion factor. Okay. I wanted to ask about the distortion factor. So DF is distortion factor. If you go through the definitions, which are in the slides of week 2, you will see. So this was your distortion factor, and your distortion factor is 0.9. Okay, got it. People also call it as G. Okay, so your G is 0.9. This is for a single phase. Yes, okay. Okay, so we will move ahead. If you have any doubts or you want me to go slow, please do tell. Okay. Okay. Your fundamental displacement factor by definition is actually cos alpha. Okay. So whatever is the alpha or the firing angle, that will be your that defines your fundamental displacement factor. And now your power factor by definition is actually distortion factor into fundamental displacement factor. That is G into FDF. Okay. So your power factor is given by G cos alpha or 0.9 cos alpha in this case. Okay. So you got it right. Distortion factor equal to G. We derived it as IS1 over IS RMS, right? And it was 0.9. The fundamental displacement factor is cos alpha. Power factor is G cos alpha or 0.9 cos alpha by definition. Correct. So the next question was on THD. Yeah. So again, THD can be obtained from my distortion factor, and the definition is 1 by G square minus 1. Okay. 1 by 0.9 the whole square minus 1, and you will end up with 0.48, which is 48%. So this is your THD. Okay. So these are the 4 parameters which we were supposed to obtain as part of the problem, right? So fundamental displacement factor, distortion factor, power factor, and THD. Fundamental displacement factor, distortion factor, power factor, and THD. Okay. So we have obtained distortion factor, fundamental displacement factor, power factor is 0.9 cos alpha, and THD is 48%. This is for single phase case. Okay. Okay, so there is one more thing over here, and that is okay. So now you understand that okay, you have a THD, you have a power factor. When you say that you have a power factor, obviously there is some reactive power and active power that's flowing. Active power is what you wanted, but unfortunately you also got a reactive power because the power factor is not unity and your current was not sinusoidal. Correct? So what would be but that reactive power? U, right? So what would be? It is P into tan alpha. Correct? Of course, I'm talking about the fundamental, right? Only then it's tan alpha, or else you need to consider this entire power factor expression, right? So this is P into tan alpha. That's your reactor power. Okay. So any other thing to be covered here? Okay. So one more thing I think I will tell. So till this point, is it fine? We have just obtained the parameters for single phase case. If you feel that this is repetitive or you already are well aware of this, you can tell me, or we can just directly go to the problems and use the formulae. I just thought, okay, it would be better to give you the formulae so that in the actual problem you can directly substitute. Yeah, what's it time?
Sir, one question, sir.
Yeah.
Does rectifier consume, sir, reactive power, sir?
Of course. It will. The reason I told you, right? Like for example, over here you see what is the shape of this source current? It's not a sinusoid, right? So then you start talking about what is the power factor. Okay. The moment you start talking about power factor, you are also talking about reactive power. Correct? Take this case. Um, the first question. This is a rectifier, right? This is a rectifier, just a diode. Simple rectifier. You saw that the power factor is 0.707. That means that what? There is a particular Q associated with it, right? P times tan, whatever is the angle. Okay. P times tan alpha. Okay. Okay. So next will be in this circuit. I will go back to the circuit. Uh, In this circuit. So for how long these thyristors are conducting? Based on how long these thyristors are conducting, you can actually calculate what is your RMS current through each thyristor and stuff. Okay, what is the RMS current through each thyristor? What is the average current through each thyristor? Okay, so these can be computed. I average. Okay. Hmm. Anyway, but that would be, I guess, too much. So, okay, so now let's solve a problem. So what would be the problem? Question number 16. A single phase full wave rectifier. I'm writing it as FWR. It's full wave rectifier with 230 volt T hertz supply feeding power to a resistive load of 10 ohm. Place feeding. Okay. Okay. So um, for a firing angle of 45 degrees, compute a distortion factor B RMS value of the fundamental current and C power delivered to the load. Okay. So now you should be able to tell directly that, okay, so what is the distortion factor? What did we see as the distortion factor? Distortion factor was, Sidha, we calculated, right? G is 0.9, irrespective of the firing angle, correct? Distortion factor was 0.9 directly, correct? So this is done. We calculated it, right? Distortion factor definition was I fundamental component RMS divided by the total component RMS, correct? So this is 0.9. And then what was the RMS value of the fundamental current? That is 4 from the Fourier series, 4 I naught by n pi over root 2, right? N is 1. So this is the RMS value, correct? So you just need to find out I naught average and you will be done with this 4 I naught by pi over root 2. Okay, and I naught is what? I naught is P naught by R. Okay, so this B also can be solved. right? And what is the power delivered to the load? P is V naught I naught. When you find out V naught, you will of course get C, right? Simple question, right? So got this? Um, okay. So what is V naught? V naught is 2 Vm over pi cos alpha because this is a single phase. This is 2 Vm over pi cos alpha. So 2 into Vm was Vm will be 230 root 2 divided by pi times cos 45 degrees, right? So this will turn out to be yeah. So this will turn out to be 146.42 volts, right? So and then you are done. I noticed V naught upon R, and you saw that the R was 10 ohms divided by V naught is going to be 14.642 amperes, right? Therefore, the fundamental component of the current is 4 into 14.642. This was the question B, divided by n pi over root 2. Okay. So you will get this as around 13.18 amperes. And the C part was P is equal to power delivered to the load, V naught I naught. 146.42 times 13, sorry, 42 times 14.64, right? This will be 2.14 kilowatt. Okay. So I think this is fine, right? Like we calculated the power delivered, fundamental component of the RMS current, and of course the distortion factor you already know, right? Okay, so we can move on to the next question. Okay, so this is a small problem. This will be question. This will be question 17. Okay. So the question is simple. The firing angle is given as 30 degrees. Okay. And this is I'm not writing the entire question. This is a single phase full wave rectifier. Okay. Simple and okay. Just determine the power factor. Same circuit. So we just found out the power factor expression in the previous slides. So what was the power factor? Power factor we saw it was G cos alpha, right? Or 0.9 into cos alpha, which is 0.9 into cos 30 degrees. So you will end up with cos 30 3 by 2 into 0.9. You will end up with 0.78. Okay. Simple question, right? Because we derived the power factor, you are able to directly use it, G cos alpha, right? G was 0.9 in your case. Just substitute the firing angle and nothing else. Okay. Hmm. Okay. So this will be question 18. So it's a very similar circuit, just that I have a battery over here. Okay, everything else is same. Okay. So what is this? This is a full wave rectifier with an RLE load. Okay. So this question has two parts. This is part A. Okay. So the question is, you have a single phase 230 volt 50 hertz supply feeding an RLE load in CCM, continuous conduction mode. If the load current is 10 amperes, and load resistance is 0.4 ohms, calculate the firing angle alpha with a battery voltage of 120 volts. What the question? It's a simple question, right? So you have a source of 230 volts, 50 hertz, right? 230 volts, 50 hertz, 230 volts. It is feeding an RLE load and the load current is 10 amperes, right? And the resistance is 0.4 ohms and the battery voltage is 120 volts. Everything is given. Find out alpha. Okay. Okay. Okay, I'll just draw the output side alone. You had something like so this was 120 volts, 0.4 ohms. This is 10 amperes. This is your V naught. Okay. So first of all, what is V naught from this circuit? Just apply your Kirchhoff's voltage law. You end up with V naught is equal to E plus I naught into R, right? And this is in DC. That is the reason L is being neglected, right? Oh my God, what just happened? Okay, anyway. Um, so what is your V naught? V naught is E plus I naught into R. L is being neglected. Why? Because we are using DC analysis. In DC, L inductor acts as a short, right? So E is 120 given, I naught is 10 given, and R is 0.4. Therefore, V naught is 124 volts. Correct? Okay. But here we see that we have a single phase full wave rectifier, right? So what is the V naught in that case? Oh my God. The writing is going off. I don't know why. Okay, anyway. What was V naught? Oh, okay. So what was V naught? V naught was E plus I naught into R. That was 120 plus 10 into 0.4, which was 124 volt. Right. On the other hand, you had a single phase full wave rectifier, wherein the V naught is given by 2 Vm by pi cos alpha. You need to find out what is alpha. So this is 2 into Vm is 230 root 2 over pi times cos alpha, right? So equating these two, you can get alpha, right? It's a very simple problem. So 460 root 2 by pi cos alpha is equal to 124. This and these are equated. Therefore, you will get alpha as 124 into pi by 460 root 2, right? So you will end up with 53.21 degrees. Please do check it. I think it should turn out correct. Simple, right? Just apply KVL and then you get it. Okay. Okay. Got it. So this is the same problem. Okay. So now I have the part B of the problem. All the parameters are same. Okay. Just that find the firing angle alpha. Alpha if the power is flowing from load to source with same E is equal to 120 volts. Okay. Okay. And the circuit undergoes a slight modification. The polarity for E is reversed. So this is V naught. This is E. Okay. And the convention of current is still the same. Okay. Got it. So because this battery is actually no feeding to the source. Okay. This is the other way around. So you of course know that in the same rectifier, two modes are possible. One is in the rectification mode and the other is the inversion mode, right? And you are well aware that in this case, the alpha will be more than 90 degree and in this case, the alpha will be less than 90 degrees, correct? And you will see that over here, when you solve it, you need to obtain alpha more than 90 degree. This is your checkpoint. Okay, this is your checkpoint. So same way we will do, apply KVL, V naught is now minus E plus I naught into R, correct? Because E is reversed in polarity. Therefore, minus 120 plus 10 into 0.4, which is minus 116 volts. And of course, your V naught will always be 2 Vm by pi cos alpha, which is going to be 2 times 230 root 2 over pi cos alpha. So you equate these two, you will be ending up with minus 116 equals 460 root 2 over pi cos alpha. Therefore, your alpha is how much? Root 2, you will end up with around 124 degrees. Got it? Simple, same question. Every parameter is same, just that the power is going from load to source, or it is in inversion mode. Okay. Polarity for E is just reversed. Okay. 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 Mm. So we will move on to the next question. If you have any doubts or you want me to repeat something, you can of course tell. So um, so this will be question number 19, right? Right. So this is a very simple problem. For a single phase wave rectifier, output voltage is 300 volt when output voltage is 300 volts when operated as a diode bridge. Okay. Find the output voltage when fired at an angle of 60 degrees. Got the question? The question is simple. You have a single phase full wave rectifier and they tell that it is operated as a diode bridge, means alpha is 0, right? Diode. Then the output voltage is 300 volts. So alpha is 60 degrees. What is V naught? Right? So what is V naught in the single phase full wave rectifier? So V naught is 2 Vm over pi cos alpha. Correct? Or you can tell V naught is proportional to cos alpha. Right? V naught is proportional to cos alpha. Therefore, V naught 2 over V naught 1 is equal to cos alpha 2 over cos alpha 1. So V naught 2 is 300 into cos 60 divided by cos 0, which will be cos 60 is 1 by 2. So you will be ending with 150 volts. Simple, right? So this is a very simple problem, I guess. Just you're just scaling it up. Hmm. Okay. We'll move on to the next question. Question 20. Okay. So single phase 230 volt 50 hertz supply. Okay, I'm just writing the parameters. Load resistance R is 10 ohms. Okay, and alpha is 45 degrees, firing angle is 45 degrees. Assume continuous conduction. Okay, and the converter is a single phase semi converter. What is a single phase full wave semi converter? You have thyristors over here, and then you have diodes. Correct. This is your load, right? I think you may be aware of, well aware of this. Okay. Find so let me be. I'm sorry. So I think I made a mistake here. So this is something like this. In a semi-converter, you have this freewheeling diode. Yeah. Sorry for the mistake. Okay, so you have a full bridge and then you just have the freewheeling diode. Okay, so find the output voltage, right? Output load current. Find the load current. Okay. And then, yeah, so this should be interesting. Find the average current through the freewheeling diode and find the RMS value. Okay, no, no, not required for the RMS value. Just find these, right? Okay. So what is the output voltage? V naught. In a single phase semi converter, V naught is going to be Vm by pi into 1 plus cos alpha, right? Single phase semi converter, V naught is Vm by pi into 1 plus cos alpha, which will give you Vm is 230 root 2 over pi into 1 plus cos 45, right? So Vm by pi into 1 plus cos alpha. So cos 45 is 1 by root 2 plus 1 into 230 root 2 by pi. So you should end up with around 176.4 volt. Correct? If you get a different answer, please do stop me and tell me. Yeah. And what is the output current? I naught is V naught by R. So 176.4 whole divided by R is 10 ohms. So 17.64 amperes. Okay. I think this is a pretty simple problem. So you found out the output voltage using the Vm by pi plus cos alpha, and I what is this, right? So the next question is, okay, find out the average current through the freewheeling diode. Via freewheeling diode. Okay. And you can also find out what is the average current via the SCR or the thyristor. Okay. So when will the thyristor conduct? Note that each thyristor will conduct from alpha to pi, right? It will conduct from alpha to pi. So one thyristor will conduct from alpha to pi. So when will the freewheeling diode conduct? It will conduct from 0 to alpha during the pi interval and also from pi to pi plus alpha. Correct? So this is the conduction, right? If you see the normal operation, so this was your circuit. So you will see that this will conduct from alpha to pi, alpha to pi. This will be from pi plus alpha to 2 pi. This will also be from pi plus alpha to 2 pi, right? And so this freewheeling diode will conduct during this alpha period, 0 to alpha and pi to pi plus alpha. Got it? So the thyristors are conducting from alpha to pi and then pi plus alpha to 2 pi, right? And the freewheeling diode is conducting from 0 to alpha and pi to pi plus alpha, correct? So from this you can find out, right? Even the RMS and the average both you can find out. RMS and average both of them can be found out. So for one thyristor, if I consider this particular thyristor, the entire cycle of 2 pi, it conducts from pi alpha to pi, right? Therefore, on time of each thyristor is how much? Pi minus alpha, right? Pi minus alpha out of the entire 2 pi interval. And on time of the freewheeling diode is how much? 0 to alpha, right? So alpha out of every pi interval, correct? For every pi interval, it is on from 0 to alpha, right? And this is for every 2 pi interval, it's on from pi minus alpha to alpha to pi, right? Okay, so from this, the RMS and average currents can be found out. Okay, so so let's say the average current I thyristor average. So what will be the average? This will be I naught into T on by T. That is the total period, right? So I naught into what is T on? Pi minus alpha divided by the total period is 2 pi, right? So uh, I naught was 17.6 amperes into pi minus what is alpha? So pi alpha is 45 degrees divided by 2 pi, right? So you should end up with around 6.63 amperes. Got it? Is this fine? If you are having any doubts, please do tell me, okay? So average thyristor current, right? This is the average thyristor current, okay? So what is the RMS thyristor current? IT RMS will be I naught into root over T on by T. That is I naught into root over pi minus alpha by 2 pi, right? That is 17.6 into root over pi minus pi by 4 divided by 2 pi. Please do it, okay? I'm not doing this. Similarly, for the freewheeling diode, the average current is going to be I naught into, it is on for alpha duration in every pi interval. So alpha divided by pi, right? So I naught into alpha is 45 degrees, therefore pi by 4 divided by pi, or I naught by 4, which is 7, which is 17.6 by 4, right? Around 4.4 amperes. Okay. And I freewheeling RMS is going to be I naught into root over the same value. Correct? So I naught by root 4 or I naught by 2, which is going to be 8.8 amperes. Got it? How to find out the switch RMS current and average current? Just determine for how long the switch is on or how long the switch is off, and you will get what is the value of the RMS current and the average current. Okay. Okay. So I think this is pretty simple for you guys. So in this question, what did we see? We took up a semi-converter. We found out what was the average output voltage, which is Vm by pi into 1 plus cos alpha. We found out the output current. And then we found out the average current through the freewheeling diode, RMS current through the freewheeling diode, average current through the thyristor, and RMS current through the thyristor. You need to find out for how long, for what duration the thyristors are on and the freewheeling diode is on. Okay. Okay. So till this point, is it fine? We just have 2-3 more problems. We will see how much we are able to cover. The other problems are given in the slides. You can just have a look later on. The solution is also given over there. But yeah, I just wanted to cover other problems, like solve problems in front of you so that it's easier for you to solve later. Okay. Okay. So if you have any doubts, please do tell. Till this point, we will have just a 2-minute respite or 2-minute break before we start again. Any doubts, anyone? You can ask. Okay. So I think this is enough about solving problems. I think it's better I go through the solutions, other slides. So I'll just skim through the other slides quickly. Okay. So far we have solved around 10 problems. Right. Okay. Okay, so a single phase fully controlled thyristor bridge AC/DC converter is operating at a firing angle of 35 degrees and an overlap angle of 15 degrees, right? The fundamental power factor is dash. Okay, so when you're talking about overlap angle, what is the point? When you're talking about overlap angle, it means that you're having a source inductance, right? So I think that was covered in the lectures as well. So you're having a source inductance. So you see that your alpha is 35 degrees and the overlap angle, as you call as mu, is 15 degrees. Okay. So what is the fundamental power factor? You would have known this as cos of alpha plus mu over 2. Just you solve it and you will end up with the answer. Cos of the cos of 35 plus 15 over 2, and you end up with 0.737, I guess. Okay. So fundamental power factor is going to be cos of alpha plus mu by 2. This is the fundamental power factor or displacement factor, right? Okay. Okay, so a three-phase bridge rectifier supplies a highly inductive load such that the average load current is 60 amperes, ripple current is negligible. Determine the peak inverse voltage. PIV is peak inverse voltage. If the line to neutral voltage is 120 volts at 60 hertz. Okay, so one thing, the current 60 amperes over here, all these values are given just to confuse you. The peak inverse voltage depends entirely on the supply voltage. Okay. So the supply voltage is line to neutral voltage is what? So the phase voltage or the line to neutral voltage is 120 volts. And of course, I told you if it's a number, it's just the RMS, right? 120 volts RMS, right? Now they have asked you what is the peak inverse voltage, correct? So 120 root 2 is your phase maximum, correct? So peak inverse voltage will be the line to line voltage, line to line voltage. So it will be root 3 times V phase max. So it will be root 3 times root 3 times 120 root 2, right? So so I think you will end up with, I think you should end up with around 294 volts if I'm not wrong. Okay. Yeah, 294 volts, right? Peak inverse voltage is just the maximum of the line to line voltage. Peak inverse voltage is maximum value of line to line voltage. Okay. Okay. Next, a three-phase bridge rectifier is supplied from a Y-connected or star-connected 208 volt 60 hertz supply. Average load current is 60 amperes again. Calculate the percentage reduction of output voltage due to commutation if the line inductance per phase is 0.5 millihenries. So this comes from the chapter about effect of source inductance. So yeah. So just find out the average output voltage of the converter, which is 3 VML by pi cos alpha. In this case, it's a diode, therefore 3 VML by pi. So the reduction in voltage is given by this factor, right? So I think this factor has been discussed in the lecture slides as well, 6F into LS into I naught, right? So just find out by how much the voltage is going to reduce and find out the percentage. Okay, find out the output voltage, find out the reduction, and then just take the ratio of these. It will give the percentage. Okay. Okay. A single phase full converter feeds power to an RLE load with R is 6, E is 60. Supply voltage is 230 volts. Firing angle is 50°. Find the power delivered to the battery. So this is something that we did. What did we do? We had a full wave rectifier. And then we said that we had a resistor and then an RLE load essentially, right? This was V naught. We solved this, right? So one was V naught is equal to E plus I naught into R. So this is one equation. The other equation is V naught is V naught is 2 Vm by pi cos alpha. Correct. So V naught is 2 Vm over pi cos alpha. So just equate 1 and 2, right? So you should be able to determine everything, correct? Just equate it. You will be able to get what is V naught, what is I. So the power delivered is the battery voltage into the current, because the question is about the battery voltage, right? Find the power delivered to the battery, right? So the battery voltage into current. Okay, so that's what they have done, E into I. Okay, so this is pretty much simple. Okay, a freewheeling diode placed across a RL load provides what? Fast turn-on times, low turn-off time, poor utilization factor, or better power factor. So you understand that the freewheeling diode doesn't allow your V0 to go negative. Less than 0 is not possible. So V0 is always greater than or equal to 0, right? That is, your V0 cannot go something like this. It will be something like this, correct? So your average output voltage is increased. So your V0 increases, correct? Average output voltage increases, which means that your RMS is also going to increase. We saw that the RMS power factor is, after all, V0 RMS by VS, correct? So it's going to give you better power factor. Okay. Freewheeling diode placed across an RL load will give you better power factor. Okay. You understand, right? Because the reason was this was the circuit. Now we have a freewheeling diode and then the load. Okay, so it provides a part something like this. Therefore, V0 cannot go negative. This is impossible. Okay, this is not possible. Right. So since your V0 is always more than 0, V0 RMS is higher, right? Therefore, your power factor is also high. Okay. Okay. A three-phase DBR diode bridge rectifier charges at 240 volts battery. Input voltage rectifier is input is 230 volt AC. Current limiting resistance in series with the battery is 8 ohms. Means that R value, your load resistance is 8 ohms, right? So your load resistance is 8 ohms. Inductor makes the load current almost ripple free. So that's what I was telling, that the inductor current is almost constant, almost ripple free. So what will be the value of the current distortion factor and input power factor? We have solved this from top to bottom. So the distortion factor is, this is for a three-phase case, right? We solved this for a single phase. For a three-phase, you will end up with a distortion factor of 0.95. Okay. So I'll just write how this comes around. Okay. So you see over here, right? So this will be your input RMS current, right? So your IA RMS will be IA RMS. The input RMS current will be I0 into, this is on for 2/3 of the period, right? I0 into root over 2 by 3. Okay. And your IA1 RMS, right? Your IA1 RMS, we saw it was G cos alpha, right? If I'm not wrong, so just a second. It will be, I'm sorry, it will not be G cos alpha, it will just be, it will be 4 I naught by n pi into, for a three-phase case, you will get sine n pi by 3 by root 2, right? Put n is equal to 1, so 4 I naught by pi sine pi by 3 by root 2, and this is I naught into root of 2 by 3. So just take the ratio of these two. IA1 RMS divided by this IS RMS, you will end up with 0.955. Okay, so the power factor is 0.955 into cos alpha, G cos alpha, right? So the answer will be this. Okay, power factor is G cos alpha. G is 0.955. This is what we got. Okay. Okay. A three-phase three-pulse converter is operated from a 230 volt supply. R is 10 ohms. Find the value of the firing angle if the average output voltage is 50% of the maximum output voltage required. Okay. So maximum output voltage. You find out what is the maximum output voltage. Maximum output voltage is obtained in the diode bridge rectifier case. So find out the maximum output voltage. And one more thing is, of course, alpha, if alpha is more than 5 by 6, alpha is more than 30 degrees, then you need to use this formula, right? So you see over here that all the values of alpha are more than 30 degrees. So you can use this formula, and if you just solve it, you will end up with the value for alpha. Okay, so I'm just skimming through the problems. You can go through it in a leisurely manner. The idea was that I wanted to solve as many problems as possible. Okay, so that's why I solved handwritten problems. Okay, so again, this is average load current computation, and the solution is also provided. Okay, so this is just HCR, a single phase, right? It's not even full bridge, it's only half wave. Okay, so the extinction angle is beta and this is alpha, so you can just find out. Okay, so it's again straightforward. Okay, a one pulse SCR control converter is triggered at an angle alpha. Load extinction current is beta. So what will be the circuit turn off time? Okay, so you understand that it is on from alpha to beta. So what is the turn off time? The period for which it is not on, it will be 2 pi minus beta minus alpha, right? So this will be the answer. And this is actually omega into t. This is the angle, right? The angle is omega into t. Okay, the angle is omega into t. Therefore, t is this by omega. Okay. So you will end up with this. And finally, again, an RLE load question. So I think you are experts in RLE load right now. Just equate to Vm by pi cos alpha with the KVL expression. So you should be get this. Okay. 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 So any doubt so far? Any other thing that you need me to explain again? The last 10 questions, I would urge you to go through it at home. So far we have seen 20 problems in the rectifiers. I think in the next week we will be moving on to other converters as well. So this is about the rectifiers. In case you have any doubts, you can of course ask me now, or else we can close the session. It's around 8 already. Okay. Okay, so then if you don't have any other questions, then I can actually end the session. Any doubts? Anyone? If you don't have any doubts, you can leave. Thank you. And yeah, have a great week ahead. Stop recording.